In this video, we're going to calculate out the rate law orders and the constant using data collected from a series of initial rates from a mix of concentrations. So here we see three different runs. We have some compound A, some compound B. They're both in solution. They start to react, and we see an initial rate, some initial change in concentrations over time. How would we go about using this data to solve our rate law? Remember that our rate is equal to the K, the concentration of A to its exponent, concentration of B to its exponent. We need those exponents to find those orders. Well, one thing we can do is we can relate two different runs. So let's look at our first two here. B is kept constant. A alters and our rate alters. I can compare both of these. I can relate them to one another. I can say, hey, that first one, the first rate and the first run's concentrations. Well, the second rate is going to have the same K. It's going to have a different concentration of A, but it's going to have the same exponent. The order won't alter. And B, in this case, happens to be the same. They're both 0.3. So we'll B2 for the moment. But what will happen is we can relate these two to each other. We can make a ratio of them, compare their rates and their concentrations, and well, since B2 is the same as B1, that whole bit cancels out. Our constants are the same. They'll cancel out. Constants don't change when you change your amounts. Constants only change if you change your temp. So my ratio of my rates is going to be dependent on my ratio of my chemical A, the only thing that changed. That change in A led to the change in rate. There was more A around, and as we see, our rate got larger. Well, let's plug this in. 0.015 is going to equal, remove all the canceled parts, 0.2 to the x. And on the bottom, 0.030 was going to equal 0.4 to the x. We can set up our ratio of our rates and concentrations. The only variable we have here is the order. If we do the math on both sides, 0.5 is going to equal, if you remember your divisions with exponents, you can put the exponent outside and have the two things divided, which means this can also look like 0.2 over 0.4 all to the x, which is a half. So this is 0.5 to the x. Well, my ratio of my rates was 0.5, and the ratio of my concentrations was 0.5, and so x must be 1. If it was anything else, these wouldn't be equal to 0.5 to each other. So the only way this is true is if x equals 1. Basically, I doubled the concentration of A, and I got double the rate out. Twice as much of it around to bump into stuff, twice as many reactions per second happened. And so we've solved one. We solved the x. Well, we can continue doing this. Now that we know that, we can use any of these and look for a change in B so we can see how B affects the calculation. And so let's do 2 and 3. Well, same A's will cancel out the same way we had the B's cancel out last time. What we'll find is that the rate of 2 divided by the rate of 3 must equal, well, again, it would have been a K on both of them. Would have been A for run 2, A for run 3, B for run 2 to the Y, and B for run 3 to the Y. Well, the K's are the same. And we know that compound A has the same concentration here for run 2 and run 3, so those parts will cancel out. And so we can cancel the A's. We don't have to. We actually do know the X value now. It's to the first, so we could put them in and do the calculation. It just isn't necessary they'll cancel out. They're both 0.4. And then our rates are going to be equal to our ratio of our B's. So the ratio of our rates, 0.030 over 0.120, is going to be equal to 0.3 to the y over 0.6 to the y. Well, 0.03 divided by 0.12 is 0.25. That's going to be 0.3 over 0.6 to the y. 0.25 is 0.5 to the y. So what does y have to be so that the right side would equal 0.25? Y has to equal 2. 0.5 times 0.5 will give me 0.25. So y must be 2, which means A is first order and B is second order. The only way to know this, however, is to have looked at this data and run these ratios. There's no way to look at the balanced reaction if we had a balanced reaction for these chemicals and know that these orders were first and second, and that the overall reaction would be the sum of them third. So this is a third order reaction overall, first in respect to A, second in respect to B. Now that we know them, we can also solve K. So my rate is equal to K, A to the X, B to the Y. Well, we now know some of these, so let's pick 0.12 is equal to K, 0.4 to the first, 0.6 to the second. 0.12 divided by 0.4 divided by 0.6 squared. 0.0333. If we want to think about units here, well, my rate, well, we've left them off, is in moles per liter per second. How much for a volume in a second? And my concentrations were in moles per liter and moles squared per liters squared. So as we divide these across and cancel things out, what we'll find is that for our third order reaction, this will be liters squared over moles squared per second. And so by using carefully selected data from several runs where we modify one concentration while keeping another constant and observe the change in initial rates, it is fairly easy to calculate out the orders of a reaction. Later in mechanisms, we'll discuss why these orders are as they are, but here's how we can find them experimentally.